Hi, and welcome to this introduction to SolidWorks Simulation. This is the first video in a video series where we will get familiar with the SolidWorks simulation software and learn how to analyze and set up different types of problems. My name is Carl-Johan and I'm going to take you through this video series. In this first video, we will have a look at the different main types of simulations you can do in SolidWorks Simulation. We will introduce the basic principles of the finite element method with some easy to understand examples. We will have a look at the basic workflow in SolidWorks Simulation, as well as some useful terminology. To round off, we will learn how to start the program, where to find the tools, and some useful settings. Let's dive in. So here is an overview of the different types of analyses that you can do in SolidWorks Simulation. There are more, but these are the main ones in my opinion. First, we have the static analysis. This is linear static analysis where displacement, stresses, strains, reaction forces, and many other things can be calculated and plotted to analyze a model. This is also the type of analysis that we're going to use in this video series. In the fatigue module, we look at the effects of cyclic loading over time and the damage done to the material because of that. Fatigue life to failure can be a useful metric to determine the expected lifespan of your component. The frequency module calculates natural frequencies and modes of your structures. This can be useful for analyzing components and structures that operate in vibrating environments, for example cars or other vehicles, or machines such as milling machines or 3D printers, to make sure the component or structure doesn't have a natural frequency close to the operating frequency of the vehicle or machine. In the thermal module, you can calculate the temperature distribution and heat fluxes in a component. This can be useful when displacements and stresses that occurs due to thermal expansion of the material needs to be analyzed. Besides failure because of high stresses and plasticity in the material, buckling is another mode of failure. In the buckling module, you can calculate the buckling modes or shapes, and the buckling load factor, that is basically a factor of safety to buckling. In the optimization module, you can perform parametric optimization. For example, minimize the weight of a structure by changing specific dimensions given certain constraints like a maximum displacement or stress. In the drop test module, we can analyze what happens to a product if you drop it on a virtual floor. In the nonlinear module, we can add nonlinear phenomenon to the simulation model. This can be in the form of nonlinear material models that incorporates, for example, plasticity. It can be large displacements, contacts, or sequencing of loads in the simulation. The dynamic module is basically used to evaluate the impact of transient loads that changes over time. An example could be what happens to the suspension of a car driving over a speed bump. All of these types of simulations are based on the finite element method. The finite element method is a numerical method for solving differential equations. In engineering, most problems can be formulated as differential equations, so it's especially useful for engineers. Also, as a numerical method, it's suitable for using a computer to carry out the calculations. Most of the time, solving the differential equation analytically is impossible, and instead we approximate the solution with a system of simpler equations. Most of the time, we will solve 3D problems and the associated partial differential equation. In this example, we have a one-dimensional equation whose correct analytical solution is the red line in the graphs. To the left, we've tried to solve this equation by approximating the solution with two straight lines, or linear elements as they are called in the finite element method. The method is set up so that it finds the best solution for the endpoints of the lines, or nodes as they're called, so that the error or deviation between the blue lines and the red one is as small as possible. In the right graph, we solve the same equation using 6 linear elements instead, and as you can see, the accuracy of the solution is much better. The downside is that more elements mean more calculations for the computer, so there is a sweet spot for how many elements you want to use. For the CAD models that we are solving, we're mostly in 3D, and the domains of our equations are the 3D CAD models. So when we want to calculate the displacements of some component under load, It's the component we divide into finite elements and solve the differential equation for elasticity in that domain. So, the 3D model is divided into elements. These can be in the form of tetrahedrons, triangles, or lines in SolidWorks. This process is called meshing, and all of the elements together are called the mesh. Each element has a number of nodes, just like we saw in the previous slide with the lines, and each node has a number of degrees of freedom, or DOFs for short. These are the unknowns that we're solving for. In the case of elasticity in 3D, using the tetrahedrons in the picture, the degrees of freedom are the displacements of a node in the x, y, and z direction. Each degree of freedom also corresponds to one equation in the big system of equations that the computer is solving. Another approach to get better accuracy for our solution is to use more advanced elements instead of more linear elements. In this case, we use 2 second-order or quadratic elements and can see that we get very accurate results with fewer nodes. In the same way, there are different types of elements in SolidWorks Simulation as well. First, we have our tetrahedrons, called solid elements in SolidWorks. These come in 2 types. The first order or linear version that has 4 nodes in the corners, and the second order or quadratic version that has 10 nodes. The same goes for the shell elements that are used for surface geometry. The first order element with 3 corner nodes and a second order element with 6 nodes. Lastly, we also have the possibility to use beam elements for long parts with constant cross-section. To set up and solve these simulations in SolidWorks, there are a couple of steps that you go through. This is an overview of the workflow in SolidWorks Simulation. We assume here that we already have a CAD model of our design. But most CAD models are too detailed and usually have a lot of small fillets and other features that take a lot of unnecessary time to mesh and solve. So to save time, we simplify the model and remove small details and features that don't affect the results in any significant way. Then, to set up the simulation, we apply material properties, define loads and boundary conditions, and create the mesh. After that, we send it to the solver, and the computer does the solving. When that's done, we can extract the results that we're interested in the form of plots, graphs, animations, and so on. So, let's have a look at SolidWorks Simulation. This is just SolidWorks with an open part. SolidWorks Simulation is an add-in that you have to start before you can access it. You do this by going to the drop-down menu at the top and select Add-ins. Then you check the left checkbox for SolidWorks Simulation to start it. And then click OK and the program will start. We get a drop-down menu at the top with all the tools and features. We also get a tab here in the command manager, and once you create a new analysis, you can access the tools and features through there as well. First of all, let's take a look at some options and default settings that are good to configure before we start using the program. Go to the drop-down menu at the top and select Options. Here we have system options like search paths, color settings, among other things. But we're going to make some default options. These are the default settings for new studies, as simulations are called, that we create in SolidWorks Simulation. So for our purposes, we do the following settings. For units, we would like to set the units for stress to be megapascals, as that is the unit we're mostly going to use. Under results, we have an important one. When we solve a study in SolidWorks Simulation, it creates some result files. It's important to keep these in order so we don't mix them and they get lost, deleted, or overwritten. Because of that, my opinion is that the best system for this is to create a new subfolder inside the folder of the SolidWorks CAD file. We can let SolidWorks Simulation do this by selecting SolidWorks document folder and then check under subfolder. I like to name the folder results. I'd also like to point out that the results folder should always be located locally on the computer that solves the study. If it's not, big chunks of data will be sent over the network during solving, and that will be slower for both you and potentially others that use the network. You can encounter permission problems and other things as well. So in our case, that means that we should always have the SolidWorks CAD file locally on the computer that solves the SolidWorks simulation study. If you want to have the files on a server or another place for storing later, you can just move it there after solving is done. For the default solver, I like the automatic option. There is a couple of different solvers for the simulations we create, and if we set it to automatic, SolidWorks Simulation chooses, based on a number of different criteria, what it thinks is the most efficient one. We'll not talk about the specifics of the solvers now, but we'll cover it in later videos. The last setting I want to change is for the color chart and the number format. So let's click color chart, and then for the number format, I like to set it to floating. This will make SolidWorks Simulation use regular decimal numbers. Then we click OK. And now we're all set up to create our first SolidWorks simulation study. Thank you for watching. Bye.